Okay, thank you, Mary. Thank you, Commander, for having me as the last speaker today. So, hello everyone. I'm going to introduce our soil moisture products system. We call it SMOPS. We want to thank our collaborators from NOAA, NASA, USDA, including Dr. Michael Koch, as well as Monash University and the University of Maryland. So in the past a couple of decades, there are so many satellite soil moisture products coming out, but these products vary significantly each other, including their characteristics, including their archived formats. So we at NOAA NESDIS developed SMOPS to provide a one-stop shop for all of the satellite soil moisture products. So currently our SMOPS are including three kinds of products, three kinds of blended products. The first one is a near real-time SMOPS. We call it SMOPS NRT. The latency for 6-hourly SMOPS NRT is only 3 hours, so that it can meet the data requirements for weather-focused users. Especially, we can deliver data to our users before the time cutoff. The daily SMOPS NRT yields the latency is only 24 hours. The special restriction is 25 kilometers. And we also reprocessed our SMOPS to generate a climate data record starting from the year of 2002. The version 1 latency is about 1 year. Currently, they are going to upgrade into version 2. The latency is about 48, basically 2 days. And the special restriction is also 25 kilometers. And we are also developing high resolution SMOPS. The special resolution is only 1 kilometer. So here's the website, as well as the daily and the 6-hourly examples for our SMOPS NRT. So what makes our SMOPS unique is it also provides the blended data layer. So given this kind of data products, we want to compare its advantage and disadvantage in comparison with the traditional individual satellite products. So here is the zonal average special resolution, special coverage for SMOPS, SMOPS, MAP, AMSA2, SCAD-A, and SCAD-B, suffering from basically 2 to 3 days revisit time. So we can find the special coverage for individuals, basically 50 to 70%, but our SMOPS can yield about 90 or even 95% special coverage. So especially in a data simulation system, when your observational data are not available, actually, then the system is conducted open run without the data simulation. So even if your observations are available, the DA run will be conducted. So here we compared the NOAA model performance with benefits of assimilating SMOPS blended soil moisture, as well as individual soil moisture tools, including SMAP, AMSA2, SCAD-A, and SCAD-B here. Stations in blue color means further improved by our SMOPS blended soil moisture. Apparently, we can find that the DA SMOPS can use much better performance. So we also trying to further improve our SMOPS products. There are only 2 operational blended soil moisture, satellite soil moisture now. One is the ESA CCI, another one is our SMOPS. So as I said, the individual satellite soil moisture vary significantly each other. So we have to use a benchmark to scale them so that we can combine them together. So previously, including the currently operational ESA CCI, are still using geodesic 10 centimeter soil moisture simulations as the benchmark. But we did find big issues for geodas simulations. Here we can find the soil moisture multi-year average soil moisture patterns for cold season and warm season in the left and the right columns respectively. Apparently, geodas shows unreasonable spatial patterns with pretty wet in cold season, but pretty dry in warm season. This is actually opposite to precipitation patterns. So we eventually reprocessed our SMOPs. The primary goal of our SMOPs and ESA-CCI is all to generate long-term, consistent, high-quality blended soil moisture, but they both actually differ from each other significantly. Firstly, our SMOP CDR use the SMAP as the benchmark instead of geodas used in currently ESA-CCI. Secondly, we processed from level 1, level 2 brine temperature instead of level 1, level 3, level 4 soil moisture tables used in the currently ESA-CCI. And also our SMOP CDR connects to our near real-time SMOPs, so that they can be used to near real-time drought monitoring, hurricane tracking, as well as other related applications. So here's the calibration results for just an example. So we calibrated the M3E to the M2. We all know that M3E actually stopped the operations in the end of 2010, but fortunately, JAXA activated the slow rotation model in the end of 2012, and so that we can calibrate the M3E to the M2 using the slow rotation model data to through building the SCO models. Here's the calibration results. The correlation coefficient is pretty high on the whole global domain, including HPO and WIPO. So given the reprocessed brine temperature, how to generate long-term consistent soil moisture, and most importantly, using the SMAP as the benchmark. So we compared 6 commonly used machine learning models, including SGB, artificial neural network, regression tree, linear regression, random forest, as the GBR. So here, the solid curve indicates the evaluation results during the training time period. Basically, is from 19 to 21, while the dot line indicates the evaluations in the testing time period is from 2016 to 28. We can find that the dot and the solid line overlap each other in the same color, actually overlap each other. That means all of the machine learning models have very good memory. They all can preserve the reference data information beyond the training time period. This is actually very important features, especially for operational applications, so that we don't need to retrain the machine learning models during operational applications. So eventually, apparently here we can find that the SG model can outperform other machine learning models. So we use the SGB model to refine our M3E and M2 soil moisture. Here is the daily examples, as well as zonal average. We can find that especially for the zonal average, when the SMAP is available, basically the refined M2 overlap each other with the SMAP. When the SMAP is not available, but the pattern can still be propagated back to 2002. So after reprocessing, we wanted to take a look at how the individual soil moisture before and after, especially the climatologies, in comparison with SMAP, as the SMAP is our benchmark. Here we can find that the dotted line indicate the original individual satellite retrievals, soil retrievals, and the solid line indicate processed ASCII A, ASCII B, ASCII E, AMS2 as well as SMOS. We can find that after reprocessing, the CDF basically the individual soil moisture much closer to SMAP, resulting our small CDR has a very similar CDF with SMAP. Here's the daily examples for our small CDR. The top left is for SMAP, but the bottom is for our small CDR. You can find the special patterns are very similar, but apparently our small CDR can provide more operation information. And in the right column, we is the relationship between a small CDR and SMAP at the peaks level on the global domain from 2015 to 2023. You can find that the correlation coefficients can reach 2.96. That means basically the same each other. So here is the special coverage for small CDR as well as its components from 2002. Apparently, the small CDR can use has a much better special coverage. So here's the validation results the comparison between small CDR and SMAP. The small CDR just yield a little bit lower correlation coefficients, but exactly same rhythmic error and unbiased rhythmic error on the whole cross domain. So recently we upgraded our small CDR from version 1 to version 2. The one big change is use the different reference data. Previously we used the SMAP version 8. Currently version 1 use the SMAP version 9. We can find that basically the version of our small CDR version 1 can match the spectral pattern with the SMAP version 8 very well, while the currently version 2 can match with the SMAP version 9 very well. Here's the differences between the smallest difference for between version 1 and version 2, as well as SMAP difference between version 8 and version 9. Our small CDR can well reflect the changes for newer versions for newer versions SMAP. So given the long-term small CDR, we also wanted to take a look at the long-term soil moisture trends on the whole global domain. Apparently, it shows various dry trends, as well as we also try to check the hurricane using our small CDR. Actually, this is a very important applications as currently satellite precipitation retrievals using the high frequency microwave observations. They are very suffering from cloudy conditions. But our small CDR, using the lower microwave observations, allowing to build the look up table instead of look down table to improve precipitation retrievals. Of course, as a soil moisture, we can use it to monitor drought events. Here's some preliminary results for our high resolution SMOPs. We divided basically class domain as the 100 tiles, but each tile covers about 8 degree by 4 degree area. So we train the model using the ascending and descending range temperature separately. I would like to highlight that actually we use the K band to represent the traditional thermal infrared land surface temperature. As the thermal infrared land surface temperature also, very struggling under cloudy conditions, but the K band can penetrate the cloud, so that we can enhance the spectral coverage for our 1 kilometer SMOPs. Here's some examples before and after downscaling. The top line is for original 25 km small CDR, and the bottom line is for the downscaled small CDR. We can apparently the 1 km downscaled small CDR can provide more details in comparison with the original coastal restoration small CDR. Here's some the evaluation results on the whole class domain. Small CDR coastal restoration small CDR can yield a Jordan square as a 0.088, exactly same with SMAP, but the downscaled 1 km small CDR can yield better performance as a unbiased Jordan square root. And our small XR, 1 km small CDR can shows better performance in comparison with coastal restoration small CDR and the SMAP. Here, I don't have any exact summary here. I just provide some our FTP site here, several links for our NOAA FTP site. You can also download our data from NOAA Osmo, NOAA class. Of course, please feel free to reach out to us if you have any questions about our smokes. Thank you.
Thank you for that wonderful talk. Question about the gap in the middle, well, a couple of gaps, but the last map showed this is a comment that also explained this satellite map that creates gaps, so missing data. Go back.
So what?
I just noticed Colorado, and we're in eastern Colorado. Yeah. There's also ground data if you look at the national networks. So you were there previously.
What kind of products? 1 km, right?
That shows the gaps. It's
Just caused by the swaths.
If that's just because of the satellite.
Yeah, satellite swaths.
yes, that also have a non-regular repeat. So they're just natural gaps. A 3-day, it takes a 3-day set of overpasses to make a full map. So that's where those gaps are coming in.
Yeah.
You have great coverage in the north pole, where there's no soil, and the south pole where it's all frozen. You got 40 coverages a day. So, but in at the equator, and then you see there's some of that matching that there's regular gaps that are going to occur, because this is 1 day.
Yeah, 1 day. Daily examples. Yeah.
Any other questions?
Thank you.
Yeah, thank you, Chief.
Thank you.
We could also open questions up for anybody, any of the other speakers. I'm just going to yell because this is not working. Do we have any other question? Any questions for any other speakers? This one works. This one works fine. I'll say that remote sensing goes hand in hand with in situ data. You have in situ data serving as a cowbell and a reality check a lot of time for remote sensing data. And it calls into question what is, I'm just going to drag everybody back to the question of what is soil moisture? And what are we actually measuring with this? Because we're not measuring soil moisture with a satellite. We're measuring a response in the L-band microwave frequency, and then we run an algorithm to get an estimate, which has many other influences, including vegetation water content. L-band is the least sensitive, but it's still sensitive. When we have in situ measurements, we're measuring dielectric response, or we're measuring capacitance, or we're measuring neutron count with CRNS. So none of these are measuring soil moisture. It's when you take that actual cup of soil, and you put it in an oven, you figure out the water difference. That's giving you the dynamic water content, right? So we're all trying to estimate, and there are different assumptions made on each of these measurements, and marrying them is another way we have to harmonize at NCSMMN, bringing all this together into one story. Because if we can all communicate at the same parameter, or at least agree upon that parameter and its definition, that's how we can then carry this data to other applications more easily. Yesterday, I used the phrase, a farmer doesn't necessarily know what a field capacity is, or what a volumetric water content is, but they know the different stages of wetness for which tractor can go in the field without getting stuck. So they have the big tractor wet, they have the medium tractor wet, or the small tractor wet. And so that we all have different ways of communicating, or how deep does my boot sink when I walk into that field? So one of our jobs at NCSMMN is to document and bring together everyone to agree upon a common metric for measuring this enigma of water in the soil. So I will throw that out there if anybody has any comments. If not, you can all get snacks and be ready for poster session.